Hello everyone, I am Onat. I am a third-year PhD candidate at University of California, San Diego and San Diego State University. So today I'm going to present our paper, ENFES, Ensemble Few-Shot Learning for Intelligent Fault Diagnosis with Limited Data. So let's start with the motivation of our paper. So predictive maintenance tries to find an optimal time to schedule a maintenance. Fault diagnosis helps establishing more efficient predictive maintenance systems. So intelligent fault diagnosis basically finds and classifies different fault types in a production system using machine learning methods. But for these methods to work well, we need huge amount of labeled training data, which may not be realistic for all working conditions and all fault types due to many reasons. Few-shot learning is one solution approach which uses very limited data. Yet, the performance of a single FSL method, few-shot learning method, may change significantly with respect to baseline system. Ensemble learning can solve this problem by combining different FSL methods. So here in figure 1, we present our proposed framework, which consists of Siamese networks and our iterative majority voting classifiers. So provided pairs of sensor data, our Siamese networks provide single method predictions, and our majority voting classifier combines these single method predictions. So let's start with the first module, Siamese networks. So Siamese network is a neural network structure which contains exactly identical two subnetworks. So in our figure, in figure 2, we gave an example of convolutional neural network. So the output of these networks are mapped to high dimensional feature vectors. Then between these vectors, we calculate the distance to find out the similarity. So the output of Siamese network is the similarity score, which is nothing but the probability that two inputs come from the same category. And second module is majority voting classifier, which combines the predictions of different methods using mode functions. Specifically, we select the mode function for our work, which outputs the fault type most voted by the classifiers. So as our data set, we use Case Western Arizona University bearing data set, which is a widely used benchmark for fault diagnosis works. And there are bearings in this data set where we have different components, rolling element, inner race, and outer race, and different fault types are observed on these bearings. So experimentally, we utilize from transfer learning to show the validity of our work. It means that we train our method using one data set and test it at another one. So, and we also shared the experimental details as follows. So let's look at experimental results. So as I mentioned, we utilize from transfer learning where we select pairwise transfer learning scenarios. For instance, transfer model from A to B means that train our model using dataset A and test it at dataset B. So since we are proposing a few-shot learning approach, we use limited amount of data, being 60, 90, 120, and 150 samples, which is less than 1% of the whole training data, where we use the whole test data to show the validity of our method. So in figure 4, we have different subfigures, which shows the different number of samples. So for instance, at figure 4a, we have 60 samples transfer learning analysis. So we show our proposed method improvement over best algorithm in table 2, where we can conclude that at 60 and 90 training samples, our method improves the best method by up to 16.4% and 10.7% respectively. So we can definitely observe that at small training samples, our method improves the best and single methods predictions significantly. So as a conclusion, in our work, we propose Ensemble few-shot learning framework, due to the difficulty of selection of single few-shot learning methods, where we combine 5 different Siamese neural networks, and we combine the single prediction of these methods using our majority voting classifier. And we show that ENFES, our method, can improve the best algorithm significantly while using very limited data. Thank you so much for listening.